So an obvious question about X-ray crystallography or X-ray diffraction, I'll use those terms interchangeably, is if it provides essentially a three-dimensional representation of the atoms, why isn't it the first thing that we do? All right, if I were to want to know the structure of a substance, it seems like something that generates a picture would be preferable to having to try to figure out the structure using all these methods which don't directly give you that information. And the answer is that it's relatively tedious to do X-ray diffraction experiments. Also, it's limited in the types of materials that you can do it on. All right. So first of all, whenever you're doing an X-ray diffraction experiment, it requires a relatively the machine that's used is relatively expensive, and it's not very high throughput. Generally, you're going to have someone who's very skilled in running the machine, and it's going to take a fairly long time just to run one sample. All right. By comparison, you could run probably 4 or 5 NMR experiments per hour if you've got an NMR machine. So these other techniques here are much more high throughput. The other downside is that for you to do X-ray diffraction, it requires that your material be able to provide you with what's considered an X-ray quality crystal. All right, so that can be either easy or hard depending on the type of material that you're talking about. So what do we mean by X-ray quality crystal? All right, so a really quick example of a material that you could do this on, okay, is something like a quartz crystal. All right, so this right here is a sample of quartz, and probably the most common place you would encounter quartz is sand. All right, sand is made up of essentially just a bunch of small quartz crystals. All right, they're pretty tiny, but if you know where to look for them in nature, you can find these crystals that are really large. All right, and so what makes it so that you can do X-ray diffraction on this is that when you have a material that's in its crystalline form, its atoms are going to be in a very neatly arranged repeating pattern. So within that quartz crystal, you're going to have a repeating pattern of silicon and oxygen atoms. All right, this is just a quick view of the arrangement of those atoms, and this arrangement would continue on, in all dimensions. And you'd have literally, millions, if not billions, of these atoms in this highly repeatable arrangement. All right, and this repeated arrangement is required for the experiment to work. All right, so certain types of materials which are called network solids. All right, diamond is an example of a network solid. Quartz is an example of a network solid. These would be types of materials that you could do X-ray diffraction on. So another type of material you could do this on are most ionic solids. For example, sodium chloride. Hopefully you recall the atomic arrangement of atoms in an ionic solid is this highly repeatable arrangement, which is called the crystal lattice, where you go where you have the green atoms here would be the chloride ions. These would be the sodium ions. So this would be like a crystal of sodium chloride. All right, and so since these atoms are arranged in this highly repeatable unit, you're able to acquire this material in its crystalline form. All right, which would allow you to do this technique on it. All right, and the last type of material that you can do crystallography on are organic materials. All right, so you can do this on relatively small organic molecules, or you can do these on things as big as protein molecules, which are actually very large molecules. All right, so a classic example of an organic molecule that you can form crystals from is menthol. All right, this is a chemical. It's some people might know it as a chemical that they sometimes will put into cigarettes. It's got a very distinctive odor. but it tends to, you can form crystals from the solid, all right? And so whenever you've got an organic molecule, essentially when you form a crystal, something special happens. So in order for organic molecules to form a crystal, essentially you have to grow them, all right? And when we're talking about growing crystals, a simplified way of explaining how it works is that you're going to make a solution that contains this molecule, and then you're going to slowly let the solvent evaporate, all right? And as it evaporates, these molecules that are in solution are going to start to stack with each other, all right? They're going to stack with each other in a very orderly, organized way, and the orientation of all the molecules are going to be in the exact same direction, all right? So I can use a little bit of an analogy here to this using trays. So just to make an analogy, let's pretend that one single molecule would be a tray, all right? So usually when you have a solid organic compound, the molecules are going to stick to each other, but they're not necessarily sticking to each other in any orderly fashion, all right? So let's just make the analogy that, well, first of all, let's pretend that all three of these trays were identical, all right? So they would be the same molecule. But one thing you'll notice about this is even though they're touching each other, they're not oriented in any organized fashion. They're just kind of randomly, they have random orientations, but they are contacting each other. So this is what you would consider to be an amorphous solid, all right? But if you've ever seen trays, you probably realize that they can also be arranged in a way that the arrangement is very orderly. Okay, so notice that in this stack of trays, you have all the trays are identical to each other, but they're really neatly arranged. All right. So first of all of them are parallel to each other, and the way that they stack together, it forces them to be aligned in the exact same direction. All right. So the thing about that is this point on this tray would be directly above the same point on the tray below it, which is directly above that point on the tray below it. And this is what this is what happens whenever you get a crystal of an organic material. Okay, the thing that makes this a crystalline material is that all of those small molecules have stacked together in a very neat fashion. All right, and because of that, this is something that you can conduct an X-ray diffraction experiment on. All right. So I do want to point out that obtaining these X-ray quality crystals can be very difficult. In fact, there's some people that is their entire job. That is their skill set, is to try to form crystals from materials. All right, it requires extremely pure materials, and for most materials, if you simply want to know the structure of it, it's a lot easier just to use these established techniques. But again, if you want to get that three-dimensional picture of the arrangement of the atoms, X-ray is what you're going to have to do. So the reason that the crystals are required is that recall from the video that what allows us, the way this works is that depending on the angle that the X-rays are approaching your crystal, you can either get constructive or destructive interference, which is going to be determined by both the angle of the X-ray beam, but also the spacing between the atoms. All right, and if you don't have that orderly arrangement of repeated orderly arrangement of atoms, you're not going to get that constructive and destructive interference that's required for this technique. All right, so one thing I want to point out is that a very important equation having to do with X-ray crystallography is what's called the Bragg equation, and that relates the incident angle, theta, all right? So that's the angle that the X-rays are coming in and hitting your crystal from, and d, which is the distance between atoms in your crystal structure, all right? Lambda right here, that's going to be the wavelength of your X-ray, and n is just some integer. So once you conduct your experiment, and in your experiment, what you're doing is you're constantly changing the angle that the X-ray beam is striking your crystal, and you're seeing what angles give you that constructive interference. There's a fair amount of data to process. And what you're a lot of times interested in as a chemist is just what's the output. All right, so there's a fair amount of data processing, but the final output, at least if you're talking about organic molecules, is what's called an ORTEP diagram. All right, and this right here is an example of one. So this is what you would get back from the X-ray crystallographer. It's just an arrangement where you can see the different types of atoms, like these are carbon atoms right here. This is an oxygen atom. But from this, you can tell a three-dimensional arrangement. All right. So I just want to point out some of the common usages for X-ray crystallography. Figuring out the structure of relatively small molecules is not really what its main purpose would be. One of the major places that it's used is when you have, in biochemistry, when you have substrates which are binding to enzymes, and you want to get some sort of a picture for how molecules interact with biological molecules like enzymes. It's possible to get a crystal of that particular molecule, and the X-ray structure will give you some sort of insight as to, for example, what types of molecules could we synthesize that would interact with this biological molecule. So hopefully that helps you out. Again, X-ray crystallography, it's a fairly complex technique, but it is very powerful because it's really the only option that you would have in terms of giving a three-dimensional representation of atoms in space.